So, welcome back, and now again we will continue discussion on extension of functions to larger domains, now for a general domain. So, in the previous classes we considered a special case, namely a cube, upper half cube, and then we extended to the lower half of that cube. Okay. And now we will discuss a result. So, this is going to be an auxiliary result, but it is also set the stage for the assumptions on our domains, especially on the boundary. Okay. So, just so let me start with some preparation. Okay. So, let omega be a bounded region with boundary. So, at this stage I am not going to say anything about the boundary, this is just topological boundary. So, namely omega closer minus omega. Okay. So, that if you it is set theoretic thing. Okay. And we are given a function in and f is given in the class Hm omega, and we wish to seek an extension of f to a larger domain, and we have already seen the importance of such extensions. Then we can get smooth approximation to given f from that extension. Okay. So, that is the technique we are adopting, and so now obviously this, because there is boundary, so we have to have some conditions on the boundary. So, here is one assumption we are doing on this boundary. Okay. So, this so for each, so this is the main assumption. Okay. So, let me call it. Okay. For each j in del omega, assume that there is a function, call it f j x, defined in a ball around j of radius r. So, again that radius may depend on j. Okay. Such that, so first of all it is an extension of given f in this ball, such that f j of x is equal to f x. So, for all x in omega intersected with this r, and of course we want this same class. So, f j belongs to Hm okay. Of course, you can also seek extension in the smooth class. Okay. So, same definition. Okay. Okay. So, this is an assumption on the boundary. Okay. So, this will pay way to make some assumptions on the boundary, so that this particular assumption is satisfied. Okay. So, this is just remember this, we are going to assume this in the next theorem. Okay. So, we call Fj an extension of F into this ball, into BA. Okay. So, here is a picture. Okay. So, this is del omega. So, a J is there. So, this part, okay, this is R. So, if X is in omega, X is in, this is just an observation. So, since omega is open, so there is the small ball around X, which is again contained in N. So, we have a trivial extension of F in Bx R for some R positive, namely F itself. So, here there is no problem. The problem is only at the boundary points. Okay. Then that neighborhood may not be in omega. So, we cannot take like here F itself. Okay. So, this has to be found. Okay. So, that's going to be essentially the assumption on the boundary. So, that we will see. Okay. So, one more notation, I will just write. Okay. So, for rho positive, we already introduced this one, but so let omega rho is omega plus Bg rho. So, this is set of all x such that x minus y is less than rho for some y in omega. So, obviously, this contains omega. So, this is, let me use different. So, this is omega, and you have the dotted one, omega rho. Okay. So, with these notations, let me now state the theorem. Okay. Let I go back to original color. So, this is the theorem. Okay. So, with the above assumption, so let me not write that. Above assumption, there exists an extension f of little f in omega rho for any rho positive. Okay. Such that, again the estimates are important for us. So, that control. So, this again extension in the same class. Okay, so that Hm omega rho is less than or equal to constant times Hm in omega. So, the next task, before giving the proof, the comment is that next task is to put assumptions on the boundary, so that this condition of every point on the boundary having an extension of in the ball that around that boundary point is satisfied. Okay, with so let me of course here that thing also. Okay, so that's important. Okay, so add that. So further let me, we cannot forget the estimates. Okay, so those are Fj Hm Bj, they are all important. Okay, okay. So, the extension also should have that estimate. Okay. So, proof is a nice application of partition of unity, which we have seen earlier. So, but let me just sketch that. Okay. So, proof and these tools are also used in other parts of analysis. So, they are important. So, they are not just in PD, but in many other occasions. Okay. Okay. So, for each x in omega closure, okay, so there is an extension. Okay. There is an extension of F. Okay, so let me not write that in a ball. Let these are important. So let me just write that in a ball. Okay. B x r. So remember, this r also depends, may depend. Okay, so it. Okay. So either the extension is trivial, for example, if x is in omega, and if x is in the x belongs to the boundary, then the hypothesis gives us this extension. Okay. So thus these balls cover omega closure. Thus you take this x, a smaller one, that's also will do. This is for technical reasons. Okay. As x varies in omega bar, cover omega bar. So by compactness, so there are finitely many. So we can find x1, x2, xn and corresponding R1, R2, Rn, such that, so this B xi are I by 3 cover omega closer. Okay. And in each of these balls we have an extension of f. Okay. So, that is and given any row positive, given row positive, so we can assume this R I is less than rho. So, smaller the radius, there is no problem at all. Okay, right. So, if so now we somehow from each extension of f in these balls we want to combine everything and get an extension in omega rho. Okay. So, that is our aim. Okay. Okay. So, choose, so this is again choose f I is equal to 1 to n, an extension of f into this b I x I r I by 3. So, we cannot just define this f the extension to be f I in these balls, okay, because they may overlap. So, somehow we have to take care of that overlapping, and that is done by the partition of unity. Okay. So, let me just that is important technique. So, let me just do it once. Okay. So, choose. So, you want to just somehow sum all these f I and get the extension, that is the idea. So, choose let what I notice. Okay. Choose theta I a C infinity function such that theta I of x is equal to 1 in b x I r I by 3 and 0 outside larger ball. Okay, some x I r I by 2. Okay, so here just small figure. So, this r I by 3 and this larger one r I by 2, and here is theta I is 1 and here theta I is 0. Okay. So, we already seen how to construct this. Okay, that is why it is important to know how to construct these test functions. Okay. So, next you define, okay, another important thing, okay, this very important. So, 0 theta I. So, we are so much used to these test functions, sometimes we forget to state all the properties. Okay. So, put sigma I x is equal to 1 minus theta I x. So, sigma I does exactly the opposite. It is 0 in the smaller ball and 1 identically 1 outside the larger ball. Okay. Now, with this theta I and sigma n, now construct these functions. Construct these functions. So, this is essentially the partition of unity functions gamma I. Okay. So, this gamma 1 x is theta 1 x. So, gamma 2 x is sigma 1 x theta 2 x. So, gamma I x is sigma 1 x sigma I minus 1 x, and the last one is theta I x. Okay. So, then since each of these are C infinity functions, so then we have this gamma I is a C infinity function, okay, and gamma I of x, straightforward verification, 0 for x in union of these balls b of x j r j by 3 and j less than I, and also 0 for x outside the ball xi. Okay. These are straightforward verifications. So, more important, so we will now just come for that. So, for I bigger than 1, and this is what partition, it makes this gamma 1 gamma 2 partition of unity. So, we have this gamma 1 x gamma I x. Okay, you just write this by the definition. So, 1 minus sigma 1 x plus sigma 1 x 1 minus sigma 2 x etc. Okay. Write down all those things and you get this 1 minus sigma 2 x sigma I x. Okay. And since these sigmas, just see the definition here. Okay. So, the sigma I x, they are all one outside the larger ball. So, that implies this gamma 1 x gamma I x is equal to 1. So, partition of unity for x in union of x j r j by 3. So, now j less than or equal to 1. Okay. So, in particular for x in b x I. So, you will also know, so though several times it is said use partition of unity, use partition of unity, but when you sit down and try to do. So, there are many technical difficulties. So, at least we should do it once. Okay. With these observations, now it is just straightforward. So, define this. F of x is equal to this summation gamma I x f I x. Okay, so where this x is defined, in fact, you just see that since we have taken R I less than rho by 2 for all I. Okay, so this, in fact, this f is 0 outside. So, it is actually defined, of course, right. So, that x is in omega rho, not omega rho, but union. Okay. But that is contained in outside, we can always define it to be 0. Okay, let me not write that. Okay, just so wherever these f i's are defined. Okay, so just fill it up. Okay. So now these are C infinity functions, these are HM functions. So each one of them is an HM function. So this first one is no problem. So F is in HM omega rho, I will say. So outside that it is in fact support of F. Yeah, so the compact support, so that's support of F is in omega rho by 2 closer. Okay. And so using that partition of unity, so let me just okay. So I just want to see that F is an extension of the other properties are fine. So just see the why F is an extension of F. Okay, that is where that partition of unity comes into picture. So if x belongs to omega, okay, so each of these f i's is an extension of F. Okay, so if F, then F I of x is F of x for all I, because each f I is an extension of F. Okay. And then we may choose, given any x in omega, we can choose a particular first ball. Okay. So these are only finitely many. Okay. So then that makes F of x is equal to F x into, we may not need all the things. Okay. Just let me say gamma x j is equal to 1 to I, where I is the first ball where x belongs to. Okay. But we have seen that this is equal to 1. So this is f x. So indeed f is an extension of f. Okay, and that estimate we are looking for. So, this norm of f in Hm omega rho is less than or equal to. So, this can just say that because gamma i's are all less than or equal to or some constant, okay, no problem. This Hm in some ball, but these are all extensions of f. So, they satisfy the same. So, another big constant. So, this is f Hm omega. Okay. So, that is the required estimate, that is coming from the assumption that each Fi is an extension of f with satisfying certain this is some b. Okay. So, let me not write everything. Okay. So, it remains now to put conditions on the boundary, so that we have this this is an important assumption we are seeing on the boundary points, and once we verify that, then we get an extension, and once we get an extension, the density result follows, and then we can apply that to get the integration by parts. So, our main aim is to get that integration by parts first, okay, and then we will see what we can do further. Okay. So, next class it will be discussion on the boundary. Okay. So, I just, so these are difficult computations. So, one need to sit patiently and work it out. Okay. So, they are not as easy as are presented here, but sometimes they can be complicated. Okay then. So, we will see next time.